Thanks for coming, guys. So this project is coming out of Microsoft Research. It's a pretty big global collaboration, actually, between 4 labs. So from west to east, we've got Redmond, Cambridge, Israel, and Beijing. So the goal of this project is actually to create a hand tracking technology that's so robust that it can be used as a really nice abstraction to create next generation user interfaces. So when So when Connect was released, people were really excited about making these contactless gestures to interact with their systems, the computer systems, and their gaming consoles. But these gestures often require like a fair amount of effort to even perform. They're slightly inaccurate, and these factors combined to make the communication channel or the interaction channel that the user established with the system to be fairly low bandwidth. So you're communicating with your system rather slowly, right? So that's fine for games and some applications, but if you want high bandwidth interaction, mice, keyboards, touchscreens, these still reign the day. And what's common between all of these things? Hands and fingers, right? So why is that? Hands and fingers are very easy, low effort to manipulate, but at the same time, they're very dexterous, accurate, and subtle. So this is what allows you to get that high bandwidth interaction channel. So hand tracking kind of combines the best of both worlds. You have this like contactless interaction, but you don't have to put a lot of effort into it, and you get this high bandwidth interaction channel if it's done well. So why hasn't this become a ubiquitous user interface technology? Well, there's been a lot of work to make it so. It's been almost 40 years since the Data Glove was first released, but they're sort of obtrusive to wear, and they're not very fashionable. In 2009, there's a SIGGRAPH paper that used a color glove and RGB webcam to track the hand. That was considerably more accurate and obviously much more fashionable, but still sort of inconvenient to try to find these gloves every time you want to use your system. So since the advent of widespread availability of consumer depth cameras, stereo systems, there's been a lot of commercial systems that have come out, and there's been lots of work in academics. So there's a few citations there, but that's just a subset of what's happening in the community. So one has to ask themselves the question, with all these systems, why hasn't hand tracking become a ubiquitous technology? What's been holding it back? Well, we believe that there's really 3 challenges to widespread adoption. So first is the lack of haptic feedback. So when you're trying to interact with something, press a button in midair, you don't get that response to tell you that you've succeeded. But there's work on that. Also, it's difficult to design these interfaces, probably because we don't have a lot of experience with the technology, so we don't know what the best way to create these things are. And lastly, most importantly for me, because it's my interest, is the technological challenges. So efficiency, modeling the hand, optimization, and the mathematics. The goal of this paper is really to try to nail the last part so that we could allow people like you to get back to the first part, these first 2 problems, right? So we want to abstract away all the technological problems. So in terms of technology, what do we want from a good hand tracker? Well, we want it to just work, right? Just work. So it's got to be very accurate, pinpointing the exact articulations of each of the fingers in the hand, and we want it to be very robust. So what I mean by robustness is that it works in all poses, not just a certain subset where it's a really easy, I'm holding my hand, you know, in some high 5 pose, right? And also, we don't want it to just work in specific situations. We want to work in a variety of scenarios. So, for example, VR or AR, where the camera's behind the head, tracking your hands in front of you. We want to work in the desktop situation, where you're very close to the computer, interacting with things. We want to work in the living room, so this classic gaming scenario, very high energy, people moving around, but also low energy situations. You know, you're lying on your couch, you've lost your remote, you don't really want to get up to find it, you just want to control the system. Right. So let's look at how we solve the problem. In order to do that, I'm just going to frame it first. So essentially what we have is a depth image coming from the Connect. And what we need to do is fit our detailed surface hand model to the depth image so we can extract the 26 degrees of freedom that correspond to the hand pose. So that's 6 degrees of freedom for the global orientation and rotation and translation of the hand, and then 20 more degrees of freedom. These basically the articulations of all the fingers and the wrists that you can count in the hand and the arm. Right. So this might seem very similar to full body pose estimation, a problem that Connect did a fairly good job of providing a robust solution to already. So aren't we done? Well, let me convince you that it's still a very hard problem, in fact harder. Right? It's a very high degree of freedom optimization problem, so you can't just look at all the possible solutions and do this exhaustive search. Also, each finger in a depth image looks exactly like the other one. Right? So here I've taken 4 fingers cropped out of a single depth image. I've rearranged them. I challenge you to find the index finger there. Right? And computer's not going to do a very good job either. That means these classical like divide and conquer techniques that we use to divide up a big global hard problem into smaller local problems fail. It would be nice if we could even see all the fingers. Hands are notorious for occluding themselves. So if you turn a hand sideways, like in this image, you can only see 1 and a bit fingers, right? So it's very hard to reason about where the other ones are. Also, with full body pose estimation, it would be a reasonable assumption to assume that humans generally are not going to show up upside down. But with hands, upside down, right side up, you're going to get all these different rotational degrees of freedom. So the effective dimensionality of the problem is much larger. And lastly, as opposed to full bodies, which are quite big, hands are just really small. So you get very few pixels even landing on the hand in the image, right? Those pixels are going to be really noisy, and you're even going to get pixels where they shouldn't be, such as in between the 2 fingers there. Right. So I'll just explain how you solve this problem very quickly. We use this thing called the golden energy. And what the golden energy does, it's a function, a mathematical function, that basically takes a pose, theta, which corresponds to all these degrees of freedom, and gives you an evaluation of how good that pose is with respect to the depth image. It's called the golden energy because golden means best. And in some sense, this is the best energy you could define, right? Because it's very simple. Let me explain how it works. Given the pose theta, all it does is it renders our computer graphics hand model in that pose. So you get this rendered depth image. And then you compare it to the input depth image by basically summing over all the pixels and comparing and adding up the difference in depths, right? So if those 2 images look exactly the same, then that would be 0. And that would mean that theta is the correct pose of the hand. So all we need to do is minimize this function. Let me just do that graphically in case I lost anybody. So if we had 2 pose hypotheses, one on the left and one on the right, and I rendered these, our model in those poses, and I overlaid them onto the depth image. I colored it black where the input depth image and the rendered depth image believe that there's a background. I rendered it green where the model in the rendered image and the input image agree. And I rendered it, and I colored it red or blue where these images disagree. Then on the left, with we've got lots of green and we've got lots of black. So this could be very low energy. It's going to be a good pose. On the right, there's lots of red and there's lots of blue. This could be high energy. This could be a bad pose. So the problem is reduced to just in 33 milliseconds, which is the time you have if you want this to run at frame rate. In 33 milliseconds, you need to somehow find this theta, this pose, that minimizes this energy, or that has a very low energy. So let me just put this in the context of how the system works. So the way it works is we get the full image from the Kinect, right? You see the entire body. We use a very simple hand detector, and this allows us to crop out this region of interest. Notice that image is exactly about the same shape as the images in the previous slide, right? So this is the image that the golden energy runs on. And what we have is something called stochastic optimizer. Stochastic optimizer's job is just to hypothesize poses that might minimize this golden energy. So it hypothesizes poses, it renders them extremely efficiently in batch on the GPU, and then calculates all the golden energies in batch on the GPU. It gets the results back, and then it gets another chance to hypothesize the poses, new poses, to evaluate. So this sort of cycle continues until when? Until 33 milliseconds. We run out of time. And then you just output the pose with the lowest golden energy. So that's it. Except that these stochastic optimizers are notorious for getting completely lost. So a key component of this is a reinitializer, which has basically been trained using machine learning algorithms to try to recognize poses that it's seen before and give the optimizer a little nudge. Say, hey, I recognize this depth image as this particular pose. Could you please try evaluating some of these poses? The end result is a hand tracker that's extremely robust. You can move your hand around very quickly. It doesn't make a lot of assumptions about where the user is or where the hand is. So Jem's able to walk completely outside of his office up to about 2 meters away from the Kinect, which is where you start to basically end up with 1 or 2 pixels on each finger. Again, there's no assumption about where the camera is. So Shahram has lifted up the camera, he's waving it around, a little crazy, still works. We want to target other scenarios. So for example, this desktop scenario that the Leap motion controller operates in, this is where you're interacting very closely with your desktop. When he turns his hand vertically, though, you'll see that the Leap motion starts to fail. We also operate in this VR modality where the camera is behind his back, or behind his head, well, probably on top of his head, I guess. And he's able to control this hand avatar. And we're hoping that, when we actually plug this into VR, that you're going to get this really nice feeling of ownership of the hand model itself. And lastly, it doesn't just work for Gem. It works for lots of people that we tried it with at Microsoft Research Cambridge. So I think there's 12 people here. You might get the impression that you need to wear sunglasses for this to work. It's just, actually, we always wear sunglasses in Cambridge. Okay, so I'm just going to wrap up so hopefully we can get some time for the demo. In terms of future work, we really want to continue pushing on the technology front. So we want to reduce the computational compute load of this, because right now it's using most of a GPU. We want to decrease the latency. So when we submitted this, it was about 100 milliseconds. We've driven that down. But if we get it down even further, that's going to increase this, strengthen that connection you feel between your intentions and the actual hand avatar on the screen. We want to look at new interfaces and scenarios. So Air Guitar Hero is sort of the one that we always beat around. We're going into VR worlds, picking things up, physically interacting with the world, controlling robotic arms so that factory workers can be safe from having to touch hazardous materials. We're also quite interested in dealing with this problem with these contactless interactions where you have to hold your hand up in order to, for long periods of time, you just get quite tired. So with our tracker, you can actually have your hand pretty close to your body which makes it a lot less strenuous, right? But ideally, we'd like to even push that further, so you have the hand just like, you know, you're on the couch, you lean your hand on your leg, and you maybe double-clicking something to change, double-click your genes just to change the channel, or you swipe new movie, right? And this sort of, you know, is beginning also to attack this problem of where do we get the haptic feedback. So this idea of self-touch. We're also interested in looking at using audio cues to try to indicate when you're getting closer to accomplishing your goal, touching something, pressing a button in midair or something like this. So that's it. We're going to try to do a quick demo, I think, if Jamie could be the demo person while I answer questions. Good. See if that works.
Can I ask questions? Okay. So like I read your paper from the proceedings, and then like I was curious about the ROI procedure. Like it was detecting the like region that hand is captured, and then like that time my hand might be like near my body. In that case, my body will be also captured, right? Then how did you like eliminate those extra parts?
Right. So right now, the tracker will eventually fail if you get very, very close to your body. But to some degree, we just use a classifier that tries to classify hand pixels away from, for example, background like body pixels.
Okay. And another question is like, you used like centimeter like as the 25 and 25 centimeters, something like that. Like the region was selected in the measure of centimeter, and then how did you determine that region? Like we cannot choose the pixels. That's why I think that's why you chose the.
I mean, there's just some simple like math to figure out how big 25 centimeters would be in pixel space.
So it's like the most front pixel was considered?
Yeah, like something like this. That would work.
Okay, thank you.
Hi, Jun from KIST. Thank you for great talk. I have two questions. One is that with your model, is it possible to adapt in the interact with the real physical object? For example, if you're grasping the real curve, then is it possible to detect some these hand positions and the.
Sorry, I didn't fully understand the question.
I mean, if we grasp a real physical object such as grasping a cup, yeah, in this case it is possible to detect like this.
So if you want to facilitate interacting with objects here, the natural way to do that is just to incorporate that into the golden energy. So then you would need a model of a cup. So for known objects, this is going to be somewhat fairly straightforward to incorporate. You render the hand and you render the cup. And you add some extra parameters to encode where the cup is and what orientation is at. And then everything should just work, although you've increased the complexity of the problem.
Okay, so second question, do you have any plan to open your algorithms as open source, something like that?
No concrete plans yet, but...
Okay, thank you.
So I might have missed something because I was slightly late. Hand pulse is defined by a discrete set of classes, or it's a continuous state?
No, it's fully continuous. So it's the global orientation and translation and 20 articulations of all the figures.
But then you said in the training stage, the system figures out this is a hand pulse. It has seen before. What does that mean if it's not a class?
Well, the reinitializer is basically a machine learning algorithm that has seen a bunch of examples of depth images in corresponding poses. So if it sees a depth image that reminds the reinitializer of a depth image that it's seen before, then it will probably
you confuse me even in that sentence. It's a hand posture you have seen before. What is because it's not discrete, so
a similar hand pose, not necessarily an exact
there you go, okay.
Hand pose.
Hi, Ilya from Haifa University. What about the scenarios with two hands? maybe overlay